Swayam Prabha. Digital India. Educated India.
One particular situation that I want to look at is what we call a dry thrust bearing. What this is nothing but a cylinder against a wall. The cylinder is being pushed by a force P, and we apply a torque on this. So, I would like to know for what value of torque tau can the cylinder remain static. This is known as, what I said earlier, is dry thrust bearing. So, let us see what is happening. If the cylinder is being pushed against the wall, and if I look at the cross section at the wall, the cylinder experiences a normal force because of which it is in equilibrium. If we assume force P, that is pushing the cylinder, to be uniformly distributed over the cylinder, then each ring, I can calculate the force in each ring of the cylinder that I am making here. This ring, because of the torque being applied, tends to move, and this motion is opposed by the frictional force. However, frictional force has a maximum possible value. So, only up to that maximum possible value can one oppose the motion of, can the cylinder oppose the motion, and after that it will start rotating. So, let us do that calculation. So, look at this cylinder. And if I look at this ring at a distance r, the normal reaction of the wall on this ring is going to be the force per unit area, where capital R is the radius of the cylinder, times 2 pi r dr. Pi cancels, and I get this to be 2 p over r square r dr. And therefore, the maximum possible friction on this ring is going to be mu s times 2 p over r square r dr. The torque d tau due to this friction is going to be mu s 2 mu s p over r square times r dr, and I integrate to get the total torque, which is going to be 2 mu s p over r square integration r square dr 0 to r. It comes out to be 2/3 mu s p r. So, that is the maximum possible torque that can be generated by the friction, and therefore, the maximum possible torque tau that I can apply without moving the cylinder is going to be 2/3 mu s p r. Next, we consider a different kind of friction, a case which is known as belt friction. In this case, we consider if a belt or a rope goes over an object which is rough, so that there is a frictional force possible between them. What is the maximum possible value of this frictional force? For simplicity, we take a pulley, a fixed pulley, and let a rope go around it at some angle. So, that angle from here to here is theta 0. In this case, maybe the contact angle here is theta 0. If the coefficient of friction between the two is mu s, what is the maximum possible value of frictional force between these two? So, for this, let us take a small portion of the rope going over the pulley. Let this small portion have an angle delta theta. Let the rope be pulled by tension T1 in this direction and T2 in this direction, and without loss of generality I take T2 to be greater than T1, so that the rope has a tendency to move clockwise and the force, frictional force, is opposing it. So, here in this section of the rope, frictional force is in this direction. There is a normal reaction of the pulley on the rope. The tension in this direction is T plus some delta T, whereas the friction pulling it back is T. Now, we want to relate what maximum possible value of delta T would still keep the rope from moving, and therefore, that will give me the maximum possible friction value. Now, you see, if I calculate the normal reaction, let me make this picture again. Let us draw this line through the center of this section. This will then be delta theta divided by 2. Since the force in this direction would be balanced, that will give me N is equal to T plus delta T sine of delta theta by 2 plus T sine of delta theta by 2, and keeping only the first order term, I get N to be T delta theta. So, that is the value of normal reaction. Therefore, F maximum possible is going to be equal to mu s T delta theta. So, again making this picture, I had tension T this way, tension T plus delta T this way, frictional force this way, normal reaction this way, and I found value of N to be T delta theta, and the maximum possible delta T that I can have is maximum possible value of friction. So, therefore, T plus delta T cosine delta theta by 2 minus T cosine delta theta by 2 would give me F max, and this gives me delta T is equal to F max, which is mu s T delta theta, because T cosine delta theta by 2 cancels and cosine delta theta by 2 is roughly equal to 1, and this gives me an equation for the relation between tension and the angle is equal to T. The maximum possible value of friction is mu s times N, and this gives me the relationship between the maximum possible difference of tension that will still keep the rope in equilibrium, will keep the rope from moving under the differing tensions and under this friction. If I calculate now, as I said earlier, if there is a pulley and the rope makes an angle theta 0 from T1 T2, so that T2 is greater than T1, and the equation is dt over d theta equals mu s T. If I solve this equation by writing dt over T equals mu s d theta, integrate this from T1 to T2, integrates this from 0 to theta 0, I get log of T2 over T1 is equal to mu s theta 0, or T2 equals T1 e raised to mu s theta 0. Thus, if I apply T2, this tension, which is T1 times this number e raised to mu s theta 0, the rope would remain in equilibrium. It will not move. You see, because of this exponential, the force difference is quite large even for very small mu s. Let me show this to you by a demonstration. Here you see what I have done is taken a bottle filled with water. This is about a liter of water, so this is about 1 kilogram, and I am going to balance this with a very small mass on the other hand, which is just these bunch of keys, and you will see that the two will balance because of the friction. Let me take this pen, and if I just put the rope or the string over the pen once, you see the bottle is not balanced. It goes down. Let me increase the number of turns. I make it 2 more turns, and you will see because of the friction now the bottle is still going down, but slightly less so. If I make it 1 more round, that means I am basically increasing theta. The bottle is still going down, not balanced. Now therefore, let me increase the turns quite a lot, and you will see now that with this small mass, maybe 100 grams maximum, I am balancing a weight of 1 kilogram on the other side, and it is all because the tension difference between these two could be as large as e raised to, now for each turn I get a 2 pi turn, and therefore e raised to that many turns times 2 pi times mu, and that can balance a large tension on this side with a very small tension on this side. So in this example, what we have therefore seen is that if rope is passing over a rough object, then the tension between the two sides maximum could differ by T1 e raised to mu s theta. So as we keep increasing theta, the frictional force keeps going up, and a larger and larger difference of T1 and T2 can be balanced. I would like to point out one thing. Although for simplicity we took a round object here, this theta could be over any shape of object. For example, I could have a shape like this, a rope going over this and this edge, making an angle theta. Then also the difference in the tension between the two sides will be equal to e raised to mu theta. It does not depend on the shape of the object. It does not have to be spherical. As long as there is an angle theta over which the rope is passing over the rough surface, the tension difference between the two maximum could be this. Let us now solve one example using this. Let us take a mountaineer who is climbing down a cliff of 60 degrees. His rope is holding here, is making an angle of contact angle of 60 degrees with this mountain cliff. Two of his friends are holding the rope on this side, and the mountaineer is slowly going down. His mass is 70 kilograms, and these friends are applying a force of 300 newtons on this side. What we would like to know is what is the coefficient of friction mu s here when everything is sort of in equilibrium and the mountaineer is slowly going down. So let us look at the free body diagram of this mountaineer. He is being pulled up by tension T. There is a normal reaction of the cliff, and its weight down is 70 g. The normal reaction would be making an angle 60 degrees with the vertical, just like this angle here, and tension T, which is parallel to the mountain side, is making an angle 30 degrees with the vertical. This T is going to be equal to 300 times e raised to mu theta, where theta is pi by 3. So the tension T on the rope on the left side of this mountain top is 300 e raised to pi by 3 mu. And now under this tension and the normal reaction and his own weight, the mountaineer is in equilibrium. If I take this to be the x axis and this to be the y axis, I can write summation f x is equal to 0, and that gives me n sine of 60 degrees is equal to t sine of 30 degrees, and therefore n equals t tangent of 30 degrees. Summation f y is equal to 0 gives me n cosine of 60 degrees plus t cosine of 30 degrees is equal to 70 g. But we have already calculated what n is. Putting that value, I get t tangent of 30 degrees cosine of 60 degrees plus t cosine of 30 degrees is equal to 70 g. So, the answer we have is t tangent 30 degrees cosine of 60 degrees plus t cosine of 30 degrees is equal to 70 g. You can simplify by trigonometric manipulations and you get t sine square 30 degrees plus cosine square 30 degrees divided by cosine of 30 degrees is equal to 70 g, and t therefore is 70 g cosine of 30 degrees. T we have already calculated is 300 newtons times e raised to pi mu divided by 3 is equal to 70 times 9.8 cosine of 30 degrees, and therefore mu comes out to be 3 over pi log of 70 g cosine 30 degrees over 300. You calculate this number and this comes out to be 0.65, and therefore, with this 300 newtons when 70 kilogram mountaineer can slowly go down as if he is in equilibrium, the coefficient of friction between the rope and the mountain top is 0.65.